This is the first problem from chapter 8 on electric force and electric fields. And it says the nucleus of the helium atom contains two protons that are separated by about 3.0 times 10 to the negative 15 meters. Find the magnitude of the electrostatic force that each proton exerts on the other. And in parentheses, the protons remain together in the nucleus because the repulsive electrostatic force is balanced by an attractive force called the strong nuclear force. Okay, so here are the couple of protons. The ones in red here, and then there are a couple of neutrons. A typical helium atom contains two protons and two neutrons. It's possible for it to contain a third neutron or just one, but it always has to have two protons, and that defines it as helium. In any case, this would be the distance they're asking about between the middle of the protons. Of course, the whole thing is a model anyway. This is how we envision. Okay, I don't know how this happened here. How we envision how the nucleus looks inside. We make kind of balls or spheres and go from there. And this is, of course, the separation distance they were talking about. I'm trying to figure out my own tablet here, and it kind of tries to play tricks on me again. Boy. So here's the separation distance, d equals, let's see what that was again, 3.0 times 10 to the negative 15 meters. And they're asking for what the force is, and really the only thing we can use here is Coulomb's force, which says that the force equals the constant K times fraction bar charge 1 times charge 2 divide by, and here I have to look if they use D for distance in our book, if they use R for radius, and they usually use R for radius. And after that, it is just a matter of plugging in numbers. I think I need a lot of space here. So where it says D right here, well, that becomes my R over here. I just said D for distance, but Coulomb's law writes R for radius or distance. So plug in the numbers here, 8.99 times 10 to the 9th. And as I said, I'm trying to figure this out. Come on. And the units are really interesting for the constant. In fact, I think I'll show them in just a moment. This is not correct yet, but I'll fix it in a moment because I want to show something there. Times, well, the charge of one proton, look it up in the book. Top of my head, 1.67, right? Yep. Nope, that's the mass. Sorry about that. Where'd it go? I ought to have it memorized. Oh, 1.602, of course. I do have it memorized. 1.602 times 10 to the negative 19 coulombs. Again, I'm trying to it keeps playing tricks on me. Come on, just give me the 19 there. There we go. Coulombs times, well, the charge of the other proton, but that happens to be the same. So I'm going to shorten this here. I'm just going to make parentheses around it, and I say that's squared. Same deal. Divide by the distance squared, which is given here in this problem as 3.0 times 10 to the negative 15 meters, and that one as well squared. Okay, back to the unit for the proportionality constant K, and I actually don't have it memorized, that unit, because it is so strange, but it's easily to be figured out the force has to come out as newtons. That's why I already wrote the newtons here. And then the coulomb squared have to divide out somehow. So that unit, that constant, incorporates coulomb squared. And the meter squared have to divide out. So that's why the unit looks that way, so that the coulombs are gone, the meters are gone, and the only thing that remains are the newtons. And then I'm going to put my little underlining bar here, and I'm going to do newtons here, and of course that is for you to calculate how much that is going to be. Top of my head, if I look at that here, negative 19 and there's a negative 15, so if you use the law of exponents, then it's negative 4, but that needs to be squared, which is negative 8, and then with the 9 here it's 1. 9 minus 8 is 1, and so 10 to the first, so roughly in the neighborhood of like 10 newtons or so. Well, actually a little bit more, like 40 to 50 newtons perhaps, in that neighborhood, somewhere around there. I didn't do the calculation, you do the calculation. But actually appreciable. That's in the neighborhood of maybe 10 pounds or so. And between these tiny protons, and of course the reason is because these are really close together. Again, my thing here about 40 to 50 newtons was kind of ballpark figure. Maybe it's a little bit less, maybe it's a little bit more. You will calculate it. Okay, I just pulled this one up here on hyperphysics. It says in the parentheses, well, as the electrostatic force tries to push them apart in that neighborhood of about 10 pounds or so, well, there has to be another force that holds them together, and that's called a strong nuclear force, which has to be at least that much. So huge forces are acting inside the nucleus. And this is just a description of it. It's kind of hard to understand. You know, there's a strong nuclear force, and in the end you just have to accept that there is, because otherwise things would be flying apart, and all we would have in the universe would be hydrogen atoms, and we don't. So there must be a strong nuclear force holding together. Here they try to explain it with that, or they do explain it with that these little particles called gluons are holding the protons and neutrons together that are being exchanged, between the quarks inside the protons and neutrons. Anyway, that's just a little bit on top of what this problem was about. Okay, the next problem is, except I lost my space in my book because all of a sudden I couldn't remember the electric charge of the proton, which I have memorized for past 30 years as 1.602 times 10 to the negative 19. Anyway, new problem. It says a small spherical insulator of mass 8.00 times 10 to the negative 2 kilograms and charge plus 0.600 microcoulombs is hung by a thin wire of negligible mass. A charge of negative 0.900 microcoulombs is held 0.150 meters away from the sphere and directly to the right of it. So the wire makes an angle theta with the vertical. See the drawing. Find A, the angle theta, and B, the tension in the wire. This will become kind of involved. In fact, the problem has a double start on it. Okay, let's see what is happening here. For one thing, they want to figure out what the tension is in the wire. So what I'm going to do is, give me one moment, I'm trying to find, I think I'm going to use blue as a color. Okay, that arrow that I just put there on the very right, I just wanted to get it back on the page. So there's the tension that we're supposed to figure out. And I guess I'll label it as such. So there's the tension. But then we have to see what kind of other forces are working on here. Obviously the electrostatic force. So there's going to be Fc between these. And notice that I write these as vectors, which makes sense because they're pointing in certain directions, so that's important. So that Fc is this way here, and I wish that would be blue like I had it earlier. Oh boy. There we go. I'm going to click there, and will I get an automatic blue one this time? No, I don't. Okay. There is a third force here, and because it's hanging from a wire, it must be its own weight, so gravity pulling it down. There we go. So FW, and actually, about that T that I wrote there, I'm going to take that back. Actually, I would like to write an FT. I just noticed I do prefer to write a force as a capital F and then put indices around it. Oh, underneath, I mean. Okay, so tension, Coulomb force, and the weight. So when I add all these forces, and you could tell me what that very, very important law is that I'm using right now, respectively, because I'm recording this to myself, you cannot tell me. So obviously this is Newton's second law, where forces are added, and because everything is in equilibrium, nothing changes its motion. In fact, it's still anyway. The acceleration comes out to zero, so the net force is also zero. And that's the equation we have to solve in order to figure out what they want us to figure out. Looks easy enough, right? But we're dealing with vectors, so we have to deal with components, so x and y components, so it's actually two equations. Okay, here's the x component. And what I have in the x is the tension times cosine, and I'm going to call this alpha because if you took the previous class from me, then you may recall that I like to have the angle measured from the positive horizontal, and the reason is that that way I can always use the cosine with the horizontal and the sine always with the vertical. Okay, and then later on we'll figure out how alpha actually relates to theta, but the outcome will be just fine. We get the right result. In a vertical, we have a tension of Ft times sine alpha, and again, that's the reason why I use that. I don't know why this keeps popping up here. Somehow I still have to figure out my tablet. So times sine alpha because it's the vertical, and now the Coulomb force that acts only in the horizontal, so Fc, and then I'm going to have in the vertical the Coulomb force is 0 because it has no vertical component in this problem, and then the weight, which is 0 in the horizontal obviously, and that equals 0 because the net force is 0. And in the vertical it's the weight, that is m times g, times the sine of, and look at this one here, 270 degrees, right? Measured from the positive horizontal is 270 degrees. That's why we're getting a negative in there. And that is again is 0 because nothing is happening. And of course Fw is written as, let's see if I find some space here, Fw is written as mass times gravity, mg. Here we go. Both of these positive numbers, the negative number comes from this sine 270 degrees. Okay, they want us to figure out what the tension is. So this one here. So that's one of our variables. And they want us to figure out what the theta is, respectively. For now, I'm using the alpha. By the way, I think you can see this, that alpha equals 90 degrees plus theta, right? Because up here would be the vertical, and then this little piece in here would be theta itself, and then 90 degrees there. Okay. So actually, oh yeah, I wanted to circle that alpha. There it is. Okay, let's see where we get started. We have both variables in both equations, so we have to eliminate something here. And the easiest way to do that is to get just these parts on one side of the equation and then the other parts on the other side of the equation, and then divide, because when I divide that with only this stuff on one side, the ft will divide out. And I will divide the y by the x, and you will see in a moment why I do that. Okay, I'm not going to change the color at this point. So ft times sine alpha, that was supposed to be an I, and that equals negative fc. Notice that fc actually will be a positive number as it points to the right, but of course I brought it to the other side, so that introduces a negative. And then ft times cosine alpha equals, and the sine 270 degrees here already is a negative, so it's a negative fw. So when I get it to the other side, it actually becomes a positive fw. And as I said, now I divide both sides by each other, and that double equal sign there looks a little strange, but that's alright. And notice what happens, of course, on the left hand side. As I said, what divides out is the ft, and what is left behind is sine theta over cosine theta. Why did I do the y divided by the x? Because I saw that sine divided by cosine will give me a nice tangent. Otherwise I would have gotten a cotangent. Would be still okay, but I would have to do some more algebra. Equals negative fc over fw. And at this point I would have to plug in numbers in order to get the alpha. Of course, what I would have to do here is divide here, put a negative in front of that, and what was I going to say? Oh, take the inverse tangent of that. But instead of writing that all down, all these long numbers, I might as well do it on a graphing calculator and show you. It saves me some space here to write it down, and a lot of effort too for me to write it down with this tablet. So let's see what I get here. Okay, there's that negative. Then in parentheses, I'm going to put the 8.99. Is that really rounded 8.99, or do they do 9.00? Sorry, I'm paging. I have to actually look that up. Yeah, they keep using 8.99. Okay, to the 9th, and then times, there's that one charge, 0.6, I go back, 0.600 microcoulombs, which is -6, times 0.900, and it's also microcoulombs, also -6. Okay, notice that right here I omitted that negative, and I did so on purpose. I'm just using the magnitudes. The reason is that my Coulomb force, this one right here, is pointing to the right, and so I need to come up with a positive, and I can only do that if I use the magnitudes of these two charges. Okay, divide that by the distance between the two, and that is 0.150 meters, and that needs to be squared. Then there's that fraction bar, and in the denominator I have the mass of this one here, which I have to look up in the problem, is 0.08 kilograms. 0.0800 kilograms times the acceleration due to gravity, which is 9.8, parentheses, put another parentheses, hit an enter. I do come up with a negative, again because of this negative, and that makes sense because once I take the inverse tangent of that, it has to put me in the second quadrant where the tangent is actually negative. Let me first check that I am in degrees. I am. So I'm going to take the inverse tangent of that number. Oops, made a mistake. Try it again. I hit the wrong button. There's the answer. I hope I didn't mess up. Negative 15. Okay, it's actually putting me into the fourth quadrant. Negative 15 degrees, which means this here actually should be 105 degrees, respectively. Actually, this one here without the negative is that theta here, 15 degrees, 15.4 degrees. As I said earlier, it's 90 degrees plus the theta, and again, it put me actually into the fourth quadrant rather than into the second, so that's why you see that negative 15 there, and the other result would have been 105.4 degrees, which still makes the theta to be 15.4 degrees. So here it is. Okay, and then actually you take just one of the two equations, and let's see, what color do I have left over here, and you plug in for Ft. So you're going to do Ft equals, I'm going to use the easier one, the second one here. Again, bring that Fw to the other side, and because here it's a negative right there, it's a negative, bring it to the other side, it becomes a positive, so it's Fw respectively just m times g, and then divide by sine theta. I'm not going to hold up here with explaining the algebra, of course you should know that. Sine alpha. Oh, take that back. Now I should erase things, or should I? Because my alpha is actually 105.4 degrees and my theta is 15.4 degrees. I have to fix that, and I don't want to do the whole recording over. So let me think about this a moment. That one is actually 105.4 degrees. I put that entry there in the wrong place, and then this one here is theta equals 15.4 degrees. That's what I meant to write. And then actually here it doesn't really matter if I use the alpha of what? Let me think about this. Yes, it does matter. I have to use actually the alpha of 105 degrees because that's how I defined my vertical force Ft. And so that is going to come out to, let's see, sorry, I'm back to green here. Now that I confused myself here for a moment, I might as well finish the problem. So what was it again? 0.08 kilograms times 9.8 divided by the sine of 15.4 degrees, parentheses, enter, and the force that I come up with is three significant figures, I think is what we used. Is that 2.95 rounded? 2.95 newtons. Just let me write a 9. Geesh, that tablet. So I might as well finish the problem since I confused myself here for a moment writing down these here. the degrees. So it's going to be the tension equals 0.08 kilograms times 9.8 meters per second squared, gravity, divide by the sine of alpha, which is given as 105.4 degrees. So I have to adhere in the calculation to the alpha that I had used. Enter, and the result comes out to 0.81, what was that other decimal? 3 newtons. This problem reads, a tiny ball of mass 0.012 kilograms carries a charge of negative 18 microcoulombs. What electric field, magnitude, and direction is needed to cause the ball to float above the ground? So what we have here is that this has a charge of negative 18 microcoulombs, and it has a weight, a mass of 0.012 kilograms, which means it has a weight of roughly 0.12 newtons, and of course that is pointing down. And again, I guess I like to use blue for my force vectors. So its weight is trying to pull it down, and in order to counteract, that means there needs to be a force of the same magnitude pointing up, and that would be the electrostatic force. It sounds a little weird when it says floating above the ground, defying gravity. Well, no, in a sense it's defying gravity because there is an extra force in it, just like an airplane is above the ground, or a balloon due to its buoyancy is above the ground. In this case it happens to be an electrostatic force that is acting against gravity. Okay, in any case, let's see what we got. Oh, it says find what electric field is needed, magnitude and direction. Actually, the direction is really easy to figure out. It's a negative charge, and you learned in the book that the electric field, which I will give a different color here, just to figure out which color. There we go, I give it this color here. The electric field points from positive to negative, and that means that a positive charge would go this way because it would be repelled by the positive side and attracted by a negative side, and a negative charge would go in the opposite direction for the same reason. So the way I actually drew the arrow was correct. The electric field has to point down so that this negative charge here would experience a force that is pushing it up, and of course its weight is trying to pull it down, and if it happens to be at rest to begin with, then it will stay at rest. Just going to copy these electric field vectors here. So we have a few more. So the electric field is pointing down here, and we would have a constant electric field here with, I guess the ground being negative. Let me see if I can. I can't get the same color, purple color here. So here we have a negative all the way through, which produces an electric field that is pointing down, pushing the charge up against gravity. Okay, for that electric field, it would exert a force that equals the electric field times the charge. And because this one is not a spherical electric field, that's why I'm not going to use Coulomb's law that says F equals K Q1 Q2 over R squared, but it's a continuous field as if exerted by a capacitor plate, and the electric field given by as a vector, electric force experienced by a very small test charge placed at that spot divided by the charge itself. and so the electric field just is there producing a force, and so F equals Q times E, and that of course is the force that is pointing up. And then of course I have a force that is down, so the weight is pointing down, and that would be negative mass times gravity. Of course the negative comes out here that this arrow pointing down would be at an angle of 270 degrees. Sine of 270 is 0. And of course, in order for it to float, that nothing happens to it, again, it's Newton's second law, which says that the force exerted by the electric field, I'm going to call it E here, plus the weight equals 0 because nothing is happening. Net force is 0, and of course, again, this one is actually negative. Okay, well, then it's just a matter of plugging these in. So charge times electric field plus a negative mg equals 0. One algebra step, electric field equals mass times gravity divided by the charge, and that equals, well, this one is going to be in newtons, mass times acceleration is newtons divided by the charge, so it's going to be Newton coulombs. And then, yeah, you have to plug in these numbers. What did it say? The mass was 0.012 kilograms times 9.8 divided by 18 times 10 to the negative 6. So again, appreciable electric fields, I want to say in the neighborhood of a few thousand newtons per coulomb. Next problem. Electron in a parallel plate capacitor, which says the drawing shows an electron entering the lower left side of a parallel plate capacitor and exiting at the upper right side. The initial speed of the electron is 7 times 10 to the 6 meters per second. That is 7,000 kilometers per second or 4,000 miles per second, so really fast, like in all kinds of electronic instruments. The capacitor is 2.00 centimeters long, very short, a little bit less than an inch, and its plates are separated by 0.150 centimeters, so that's just a little bit over a millimeter. Not to scale apparently, because this one here is about 15 times longer than what this one is high here, so it's not to scale. In any case, assume that the electric field between the plates is uniform everywhere and find its magnitude. So between plates and uniform, and find the magnitude of the electric field. Okay, let's see what's happening in this problem. This one, ooh, does have 2 stars on it. All right. So the electron moves left to right, and if it wasn't for the capacitor plates, because of its inertia, it would keep moving left to right at the constant speed. But of course there's an electric field, negative down here, positive down here, the arrow's pointing down, and because it's negative, it's repelled by the negative, attracted to the positive, and so on its way to the right it will deviate from that path and make its way up, and it looks somewhat circular, but you'll see that actually it's a parabola going up. So it's just supposed to clear here. Again, we can write Newton's second law down. So we have some forces here, which would be the electric force. Again, we'll have actually the force exerted by a capacitor plate. And we could say that, well, we have gravity trying to pull it down. if this was actually vertical, it doesn't say so. Let's say it's horizontal and gravity wouldn't play a role. However, even if it was vertical, even if gravity would try to pull the electron down, I will show later when I'm done with the problem that actually the weight of the electron is so small compared to the electric force that it's totally negligible. As I said, I can only show that later. And the reason is that the electric field is relatively high in order to deviate it. Remember, it's really, really fast going through here. So you have to have a huge electric field to actually get it, push it up here. Okay, let's get started. So there is an electric force, and that will produce an acceleration. Of course, Newton's second law is mass times acceleration. The Fe here for a constant electric field would be the charge of the electron, which is simply written as lowercase e, times uppercase E for the electric field, equals mass times acceleration. And of course, one algebra step gives us the acceleration. We actually have two unknowns here. I'm going to write it as such: E times E divided by the mass of the electron. Actually, I should also write a little e right there if it lets me. If it lets me, I will write a little e right there. No. My tablet doesn't let me. There we go. There we go. Squeeze it in there. Okay, that's the acceleration. Okay, acceleration reminds us about, obviously, motion. Something is going on. And it brings us all the way back to kind of the first couple of chapters in this book, chapter 2 and 3, about the kinematic equations, where when you have an acceleration, which we have in the y direction, it's being pushed up here, we have that y equals 1/2 acceleration times t squared. Because of this t squared here, the squared, that's why I said earlier, actually that's a parabola, because that's what the square is. And in the x direction, what we have is velocity in the x direction, the original velocity in the x direction, times time, and because of its inertia, that initial velocity will not change in the x direction, and there is no acceleration in the x direction. So this one here, I'm just going to write it down for just a moment. 1/2 a t squared in the x direction. There is no acceleration in the x direction, so I can just take this off here, and I will. And of course you see that in the y direction we do have an acceleration as shown because of the electric field. And we should also have this one here, but again I'm going to write it down, v0y t times t. So the two equations, the x and the y, way back in the kinematic equations, look the same, but there's no acceleration in the x direction, so I took that term out. And there is no initial velocity in the y direction, so this term actually is not there either. That's why these equations look so abbreviated. And I guess I could say here, because I have my ay right here, I probably should also say that this is the acceleration in the y direction. ay. So I have to squeeze in another index. Okay, I'm going to plug this one in here. So this one is going to be I'm gonna back up just for a moment before I plug it in. I should note which kind of variables I have here. This here's a variable, an unknown. That's an unknown, the electric field. Well, I plug this in here. Okay. That means I still have one unknown right here. Ooh, why is it doing that? Kind of green stuff here. There's a little better. But I don't know the time, so that's an unknown either. But I have the time here, and then everything else is given. So when I substitute this one in there, and this other equation in there, I have eliminated the acceleration, and I have eliminated time. and the only unknown I will have is the electric field, because everything else is given. Charge of the electron, mass of the electron, the initial speed is in the problem. You can see the x here, 2 centimeters. You can see the y here, 0.15 centimeters. So that's why I do all this algebra. And again, this here comes from that I look at it, well, there was motion involved here, and then there's a deviation here, so there must be something happening with the kinematic equation. That's where it come from. And of course, there was a force here which produces that acceleration, so that's why I also wrote down Newton's second law. And that's why this problem here has a couple of stars, because you have to think about, well, which equations apply here. And that's why I just try to explain why there is Newton's second law and the kinematic equations in here. All right, now let me do the algebra. So this one is going to come out to y. Okay, I guess I'm going to keep the green. Y equals 1/2 E times E over the mass of the electron. There it is. Times t squared, but I might as well plug this in, so x over v0x. So x over v0x parentheses, and that's squared because that's what it said earlier. And then I have an equal, and then I plug in numbers, and if you make the unit analysis, I guess I could do it, the electron, let me try another color here, black I guess. The electron would be in coulombs. The electric field is in Newton per coulombs. The mass is in kilograms. The x here is in meters, but it's squared. And the v0x is in meters per second, but that's squared as well. All right. So as far as the units are concerned, the coulombs divide out. The newtons here divide out with 1 kilogram meters per second squared, and then there's a meter left here, divided into a meter squared, so actually the unit comes out to meters as it should here for the y. And then, oops, I noticed that actually I have to do algebra on this. This is not what they were asking for. They were actually asking for this one here. Whoops, sorry. Didn't have to do that. Well, that's all right. But actually I would have to solve for E. I missed that part, but here for a moment. So I got involved in the units. But that's no big deal. Just a lot of algebra. Let's see, how can I write this best? Okay, there's a 2. And then I'm going to write an ME right there. And then I make myself a long fraction bar. Or maybe I don't need it that long. Divide by E. And then I have a V0x squared here. And I have an x squared here. There we go. And then I have an equal. And then I have my underlined whatever I plug in there. And then I push this out of the way. And actually my unit analysis should have shown that when I put all these units, kilograms, coulombs, meter squared, meter per second squared, that eventually I'm going to come up with newtons per coulombs. And so here at this point, yeah, so actually I don't need to calculate this one over here. And technically I don't need this one either. There we go. So this one here is all given. That's 9.1 times negative 10 to the negative 31. This one here is 1.602 times 10 to the negative 19. This one here is given in the problem as what was it? 7 times 10 to the 6 meters per second, and that has to be squared. And this one here is given as 0.02 meters, and then I notice as I did the algebra, oops, forget one little thing, right? As I did the algebra, there should be a y, and the y is given as 0.0015 meters. Plug in all the numbers and you come up with the result for the electric field. Oh yeah, and then I wanted to point out why I didn't use gravity even if it was in the vertical. As I mentioned earlier, maybe I did. You come up with a relatively large electric field, and I can just give it away. It's in the neighborhood of like a few thousand newtons. So let me just use 1,000. I'm not sure what it shows. Why my graphing calculator looks so weird when I get it in here. Oh boy. Okay, so let's assume that you come up with 1,000 newtons. That's actually not too far off. It's a ballpark figure. And I'm sorry, newtons per coulomb for the electric field, and I multiply that with the charge of the electron, which is 1.610 to negative 19. And this here would be the electric force exerted on the electron, and now I compare that to the gravitational force, which is the mass of the electron, 9.1, 10 to the negative 31 kilograms, times the acceleration due to gravity, and notice what happens. That, sure, this number is very small, but it's much, much larger than this number here for the weight of it. It's 10 to the 14 times larger, so even if the deflection plate is in the vertical, the weight of the electron is totally negligible to compare to the electric force. And it's usually true of the electric force. It's much, much larger than the gravitational force. Has its reasons in that the gravitational constant itself is a really small constant, 10 to the negative 11, while the constant that you find in the Coulomb law at 10 to the 9 is relatively large compared to that. However, in our everyday life, of course, gravity is ruling everything, pretty much everything. It seems to be larger than an electric force, but the reason is that most of the things that we encounter in our everyday life are actually electrically neutral, or they have a very tiny charge, so the electric forces are really small because of the really tiny electric charges, or them being neutral, they would be zero. So that's why gravity seems to rule our world, because we always have mass, and mass always exerts a gravitational force. Let me show just one more thing. These are the problems from chapter 19, and the first one I'm going to do reads: the anode positive terminal of an X-ray tube is at a potential of 125,000 volts with respect to the cathode negative terminal. A. How much work in joules is done by the electric force when an electron is accelerated from the cathode to the anode? If the electron is initially at rest, what kinetic energy does the electron have when it arrives at the anode? So they want us to figure out what the work is, and the equation we use for that is that the work is defined, respectively negative work going from A to B is defined as either the difference in potential energy, in electric potential energy, so EPE, and I should write this a little bit lower, so I'm going to take this off again. So the difference in electric potential energy BA. Here I have to pay attention that when you look at the formula that the indices are turned in such a way, respectively the difference in potential, electric potential, times the charge. Okay, rest is actually pretty much plugging in numbers. WAB equals negative, and what we got here is an electron. Yeah, the anode, how much was the electron is X-ray, so there we go. I just had to read that again. So minus 1.6 times 10 to the negative 19. Notice the algebra step that I did of putting the negative to the other side, and of course there it is, and the electron charge itself is negative, times the potential difference. Oh, I forgot to write here the index on the electric potential, which is also from B to A, and this is given in this case here as the positive 125,000 volts. And then just plug into the calculator and you're going to come up with a positive number. And the unit is going to be joules. So there we go, and then I guess I could just plug it in and do it myself here, and I'm going to come up with let's see, 3 significant figures. Actually it's a 1.60 here times, so 2.00 times 10 to the negative 14 joules is the answer. And again, if you look at coulombs times volts, you're going to come up with joules. By the way, this was part A. I'm going to do part B in a moment. This is some X-ray tube. We have the anode here, the positive terminal, and this part here is the cathode, and it's at a 45-degree angle to the cross-section of this bulb here, this evacuated bulb, and we have this huge potential, 125,000 volts, and then the negative electrons are accelerated towards, and what did I just say where the anode is? Whoops. The anode is this one here. The cathode is over here, which is negative, so the negative electrons are going to go to the positive anode. They hit the anode, and as they hit it, they're being decelerated, and in literature the word for that is that Bremsstrahlung is produced, literally braking radiation. It's a German word that's also in English literature. So braking radiation is produced with the same energy with which the electron hit here, and that means with this energy here as well. And that braking radiation has the word X-rays. So the electron is going to come out here. It's going to hit that 45-degree target, the positive anode, and the X-rays are going to come out this way, come out of the paper here, because it's a 45-degree angle, so it's kind of like a reflection out of that, and that's how we get the electrons out of that. The 2.00 times 10 to the negative 14 joules is correct, but notice that it's a really small number, and in high energy physics we like to introduce a different kind of unit that makes it really easy to deal with. This one here is basically 125,000 electron volts. It's not a international unit in the sense of being a metric unit, that's what I mean, but it's an accepted unit within the field that abbreviates something, and you can easily see the connection here. You have potential of 125,000 volts, and you get 125,000 electron volts out of it. And then you can see that this one here is the conversion factor between the two. Okay, let's do part B. It's kind of predictable that this will be the same answer. So it says that in part B, if the electron is initially at rest, what kinetic energy does the electron have when it arrives at the anode? Well, when you look at that long equation there for the total energy, there is no rotational energy, there is no gravitational potential energy, there's no elastic potential energy, but it's pretty much electric potential energy as well as kinetic energy. And it boils down to that the kinetic energy that it will achieve at point B, which is the anode. Ooh, how did I do that? There. Is going to be, again, the difference in electric potential energy from, let's see, whoop, did it again, from A to B. And that then is the same 125,000 electron volts respectively, 2.00 10 to the negative 14 joules. Okay, and the next problem says that 2 point charges plus 3.40 microcoulombs and negative 6.10 microcoulombs are separated by 1.20 meters. What is the electric potential midway between them? So here we have one of the charges, call it Q1, at least I try. Q1 equals positive 3.40 microcoulombs, so 10 to negative 6, and the other one is Q2 equals negative 6.10 microcoulombs, and there's a distance in between these two. We call it R. You can guess why I do that, of 1.20 meters. Okay, and let's see, let me check that. Separate. What is the electric potential midway between them? So what's the electric potential right here? Well, these are point charges, so we have to look at the electric potential due to a point charge, and that is V equals K times Q over the distance R. I have to be, the way I wrote this here, I have to be a little bit careful. Actually, I will take this R away here. And again, you will see in a moment. I actually put it in here because of this R right here. That's why I wrote it. But then I realized, when I do the calculation later, the actual distance is actually half of that. So I better not call this R here. And then later on, I have R equals, well, half of 1.20 meters. So I better call it that way. Respectively, I better write it that way. Okay, that means that the electric potential midway between these two charges is V equals at 2, so K times Q1 divided by plus the potential from the other one, K Q2 divided by R. Of course, the second one, the charge is negative. So this one being positive, this one negative, actually they kind of subtract. And this R here is actually the point halfway in between, so that's actually 0.60 meters. R equals, okay, and the K of course is the 8.99 times 10 to the negative 8.99 times 10 to the 9th Newton per Coulomb squared times meter squared, proportionality constant, and then it's just a matter of plugging in numbers, and when you put all the units together you would come up with volts. Okay, and the next problem reads: the electric potential energy stored in the capacitor of a defibrillator is 73 joules and the capacitance is 120 microfarad. What is the potential difference across the capacitor plates? So the energy stored for a capacitor is given as 1/2 times the capacitance times volt squared, potential squared, equals, and you come up with something, and because as long as you put them in base units, we're gonna be in joules. The capacitance is given as 120 microfarad. That is actually a huge capacitance. That's why these things are not dangerous. That's why they're so powerful. And and then I just noticed that, of course, the voltage is what has to be determined, and the electric potential energy is given 73 joules. I kind of look over as I record this here over my left shoulder into the book, and then to the right onto my screen, and unfortunately sometimes I miss something like that, but it's easy to correct. So the electric potential energy, therefore, do the algebra on this one here, is 2 times the electric potential energy divided by the capacitance, take the square root, come up with the electric potential in volts. And I take this one off because I don't need it.